In this video, I will be talking about coordinate systems. There are many coordinate systems astronomers use to describe positions of objects in the sky or on the Earth. Depending on what we are trying to measure, we may use one coordinate system over another. Let's begin by considering the topocentric coordinate system. These are observer-dependent coordinates. They're given by z equals up, x equals east, and y equals north. That is, if you are at this point on the Earth, x will be east, y will be north, and z will be out, perpendicular to the surface of the Earth, at your position. There are also angular topocentric coordinates, which is the azimuth and altitude coordinate system. The azimuth of an object is the angle clockwise from north of your position. And the altitude is the angle from the horizon, from your local horizon, to the object. There's a nice picture here that shows these coordinates very well. Suppose you're an observer here. This is your local horizon, this entire thing. And suppose you observe a star at this point here. Then the azimuth is given by the angle clockwise from north, this way. And the altitude is the angle the object makes with the horizon, that is, this angle here. Note that most telescopes are on the altitude and azimuth mount, meaning that they move as described by the altitude and azimuth angles. Note that since these are topocentric coordinates, you have to keep telling the telescope where to point every so often. Now let's move on to the equatorial coordinate system. First, let's start out with local equatorial coordinates. This system is used to measure relative locations on Earth. Usually, it's used to measure the antenna separation in an array. Coordinates are given as follows. Z equals North Pole, x equals radially out from the pole through your longitude on Earth. And y is east. So suppose you are here, and this is the center of the Earth, just for reference. Then the z-axis is the North Pole. So it determines your height above the equator. X is radially outward from the North Pole. And y is east. Note that these are perpendicular to each other. Like I said, these are usually used to measure the antenna separation in an array. Next, let's consider the equatorial coordinate system. This is usually given in terms of the right ascension and declination, but in this case I will consider the XYZ equatorial coordinate system. These are given by z equals north, x equals out from pole at 0 degrees longitude and 0 degrees latitude. And y is perpendicular to x and z. So it's out from pole at 6 hours or 90 degrees and 0 latitude. Hence, this coordinate system looks like so. Z is the North Pole. X is out from the pole at 0, 0, 0 longitude and 0 latitude. And y is given by the one perpendicular to both x and y. This is 90 degrees longitude and 0 degrees latitude. Note that these move with the Earth, but don't depend on where you are located on Earth. Every position on Earth can be determined in this coordinate system uniquely. There are also precessed equatorial coordinates. These are a little bit different, and they take into account the fact that the Earth precesses every 26,000 years or so. Next, I'll consider the imaging coordinates. These are usually denoted by U, V, and W, and they're used by radio astronomers to make an image of the sky. They are discussed further in the interferometry lectures. However, here I will just state what they are. U is locally east of the observer. V is locally north. And W is toward the source.